All right, welcome to my lecture on the central limit theorem, and we're specifically going to apply the central limit theorem to sample averages. Okay. So the sample average is just taken by adding up all your data, which will be your observations x1 through xn. Just add them all up, divide by the number of observations. That's your sample average. Okay. And the central limit theorem states that if we have a random sample of observations represented by x1 through xn, and they have a mean with mu sub x as their mean and a standard deviation as sigma of x, then the sample average x bar has a normal distribution with mean equal to mu of x and standard deviation. And this is key. This standard deviation changes. It's the old standard deviation of x divided by square root of n. And there is a stipulation in order to use this. So in order to use that x bar is normally distributed, either you need a sample size of at least 30, or the original data set needs to be normally distributed. Okay, so if you have a sample size of 20, say, and if you have a sample size of 20, then you can use the central limit theorem only if this original data is normally distributed. Okay. So here's an example of the central limit theorem, and it's a similar example to what we did in our lecture on the normal distribution. It says the heights of men are normally distributed with a mean of 68 and a standard deviation of 5 inches. We'd like to calculate the probability that in a random sample of 25 randomly chosen men aged 25 to 35, the sample average has a height between 67 and 70 inches. Okay, so let me add that. Okay. Now, we can use the central limit theorem because our original data, the heights of men, are normally distributed. If this data was not normally distributed, we'd need a larger sample size. Okay. Now, the sample average, according to the central limit theorem, is the original mean of 68 inches. But, very key here, the standard deviation has changed. The standard deviation was 5 inches, but the sample average has a standard deviation that takes this number of 5 inches and divides by the square root of n. N is 25, so I have 5 divided by square root of 25, that's 1 inch. Okay. So if I want to calculate that someone is between 67 and 70 inches, well, this is the probability the average is between 67 and 70 inches. The average is normally distributed by the central limit theorem. So I'm going to proceed as we would before. I'm going to take the probability x bar is less than 70 minus the probability x bar is less than 67. And then we take the z-scores of each. So I subtract by the mean of 68. I divide by standard deviation of 1. I do the same for 70. I subtract 68, I divide by 1. Okay. And I apologize, this probability, I need to take the probability of the larger and subtract it from the smaller. So the larger is the 70. Okay. So there we go. So this has a z-score of 2, that's correct, minus the probability z is less than -1, that's 81.8%. Okay. So very key here is that I'm dividing by 1 because that's the new standard deviation. Okay. Now I could use a calculator if you'd like. Okay. And here's the normal distribution calculator. So the mean is 68 inches. This is 1. I want to calculate its between, and the values that's between are 67 and 70. So 67 and 70. Let's recalculate that. That's 81.8. And that's exactly the probability we have. So you can do the z-scores in the table, or you can use an online calculator. Okay. And the one thing I cannot emphasize enough is that this standard deviation changes, and it changes according to this. That's how the standard deviation changes. Okay, let's do another example. We've seen this graph before. Okay, here's the summer temperatures from 1951 to 1980. Then here's the histogram of the summer temperatures from 2005 to 2015. We can see that temperatures are normally distributed in both graphs. They've been overlaid, right? Okay. Now, according to this graph between 1951 and 1980, the sample average lies somewhere in here, whereas between 2005 and 2015, it lies somewhere in the middle, right here. Okay. Okay. So these graphs show the histograms for each time period are approximately normal. The average temperatures are represented by about where the peak would be in the histogram. And most temperatures fall around average with some extremes and equal proportions falling above or below. Okay. The amount by which the data point varies above versus below is represented by the standard deviation or variance. Okay, and from the histograms we've seen that the means have increased over time visually. Okay, so here's our problem. We have a population average from 1951 to 1980. So this is hypothetical. Let's suppose it's 58 degrees. Okay, in springtime in a certain area. Okay, and let's suppose that the standard deviation is 12 degrees. Okay, and if the population mean and standard deviation have the same, what are the odds of obtaining a sample average of 61.5 degrees or more in a sample of 36 springtime temperatures? Well, I want to emphasize that we're going to use the central limit theorem. So we're going to say, hey, maybe temperatures haven't changed since 1951 to 1980. We have all the data in the past. And I want to emphasize this is hypothetical. I made up this example. So let's calculate the mean, and suppose we found it's 58 degrees with a standard deviation of 12. Okay. Then what I can do today is I can take a sample, and let's say I took 36 samples of temperatures at a specific time, and I found that the sample average was 61.5 degrees. Well, if indeed the temperatures has not changed and the population mean is 58 degrees with a standard deviation of 12, what are the odds of seeing a sample average of 61.5 degrees? Well, I can use the central limit theorem to answer that. Okay. So I have a large enough sample size that I can use the central limit theorem. Okay. And we can see with the central limit theorem that the mean is 58 degrees. My apologies. And the standard deviation, this is key. That's what changes. It's the original standard deviation of 12 divided by square root of n. N is 36, so 12 divided by root 36 is 2. Okay. So I want to calculate, I get a sample average of greater than 61.5 degrees. So I do the z-score and I do the complement rule if I'm using the tables, okay? So I do 1 minus the probability. I take 61.5 minus 58 degrees. I divide by its standard deviation. And remember, this 2 comes from the central limit theorem. And when I do that, I get 1 minus the probability. Z is less than 1.75, which is 1 minus 0.959, or 4.1%. Okay. So the odds of seeing an average temperature that would be 61.5 degrees or larger if things had not changed is 4.1%. Okay. And I want to emphasize this was just this data in this example starting here in this example was made up. The discussion in this graph is real. That came from the New York Times, as well as this discussion. Okay, so the next thing that I'm going to talk about is using the normal distribution to calculate sample proportions, but that's going to be another topic. That concludes my lecture on sample averages, in which your data is numeric. Okay, thank you very much.